Solve one problem on damped vertical shaft with single rotor. Given question: a horizontal shaft of 10 mm diameter is simply supported at both ends by bearings. A rotor of mass 5 kg is attached at middle of the horizontal shaft. The span between two bearings is 500 mm. The center of gravity of rotor is 2.5 mm offset from the geometric center of the rotor. The equivalent viscous damping at the center of rotor shaft may be taken as 52 Newton-second per meter. Find the deflection of the shaft and critical speed of the shaft. Assume E is equal to 200 into 10 raised to 9 Newton per meter square. Speed of the shaft 720 rpm.
Let us understand given data with the help of diagram. Diameter of the shaft small d is given 0.01 meter. Mass of the rotor m is equal to 4 kg. Span of the shaft in between bearings, that is L, is equal to 0.5 meter. Center of gravity point from the geometric center is given, that is distance in between points S and point G, that is E is equal to 2.5 into 10 raised to minus 3 meter. Then the damping coefficient. So it is also given 52 Newton second per meter. So this is the question for the damped vertical shaft with single rotor. Then modulus of elasticity 200 into 10 raised to 9 Newton per meter square. Speed of the shaft. So we will consider here the shaft rotates with angular velocity omega 1. So when it rotates with omega 1, then we will consider the speed of the shaft N1 is equal to 720 rpm. Now we will move to the first question. We have to find out critical speed of the shaft, that is NC. So we know that at critical speed shaft rotates at its natural frequency. So we have to first find out omega C. So omega C is equal to omega N. Because at critical speed, that is omega C, the shaft rotates at its natural frequency, that is omega N. So how to find out this omega N? So we know that omega N is equal to under root of K by M. Where mass M is mentioned 4 kg, but the stiffness of the shaft is not known. So we have to first find out this K. Now we know that the stiffness K of the shaft is equal to W by delta. So delta is the static deflection in the shaft. So we will first find out the value of delta. Now in question it is given that shaft is simply supported. So for simply supported shaft, we have formula for delta is equal to WL cube by 48 EI. But K is equal to W by delta. So we will put the value of delta here, that is WL cube divided by 48 EI. Then this W and this W is getting cancelled, and when we simplify that we will get K is equal to 48 EI by L cube, where E is the modulus of elasticity that is mentioned in the question. We have to find the value of I. So value of I, we have the formula pi by 64 into 0.01 raised to 4. That is the inertia of the shaft. Then that is 0.01 is the diameter, that is pi by 64 d raised to 4, and L, that is also mentioned in the question, 0.5. So we have to take 0.5 cube. So when we solve this, we will get the answer for K, that is the stiffness of shaft, is equal to 37.69 into 10 raised to 3 Newton per meter. Omega N is equal to omega C, which is equal to under root of K by M. So when we put value, we will get the answer 97.08 radians per second. Now we have to find out critical speed, that is NC. So we have relation omega C is equal to 2 pi NC by 60, and therefore NC is equal to 927.05 rpm. Now we will move to the second question. We have to find out deflection of the shaft. Now when this shaft rotates with angular velocity omega 1, then there is the deflection in the shaft. That is, this geometric point, that on this geometric axis point S is getting shifted by a distance y because of the rotation of the shaft, and that's why we have to find out this value of y. So if we observe this question, viscous damping is provided. So we have to apply the formula for the damped shaft, and we have formula y by E is equal to r square into magnification factor. And for this magnification factor ohm, we have formula 1 divided by under root of 1 minus r square bracket square plus 2 zeta r bracket square. Now we can understand here, to find out the value of y, we have to first find out the r, that is the frequency ratio, and we have to also find out zeta, that is the damping factor. Now E, that is this deflection of point G from this point S, is mentioned in the question. So first we will find out the frequency ratio r. So r is equal to omega by omega n. Now for this question, the shaft rotates with omega 1. So we can say that omega is equal to omega 1 and omega n is equal to omega c. So which is equal to, here we will take n1 by nc. So n1 is 720, nc is 927. So here ratio is 0.7766. Now we will find out damping factor zeta, which is equal to c by cc. So here coefficient of damping C is mentioned in the question, that is 52, and critical damping coefficient Cc is not mentioned. So here it is the formula 2 under root of K into M, where K is the stiffness, and which is 37.69 into 10 raised to 3, and M is the mass, which is mentioned in the question 4. So when we calculate this, we will get the zeta 0.0669. Now we can put this value of r as well as zeta, and we can calculate the value of y. Therefore y is equal to 3.67 into 10 raised to minus 3 meter. So we can say that it is equal to 3.67 millimeter.